Hello there. We're going to talk about paper chromatography today, the theory behind it, not the actual doing. That is another video I have already made, and ideally you have watched that video before watching this one so that you get both how it's done and what it tells us and able to put the two together. So this is really the second video in a series on paper chromatography. But what we're going to talk about today actually applies to like all types of chromatography. Does not have to be paper chromatography, thin layer chromatography, gas chromatography, high performance liquid chromatography. There's even new chromatography since I last studied it in college. So lots of forms of chromatography. They're all based on the same basic principles. They're just different ways of carrying out those principles. So we're going to look at paper chromatography and just know that it could apply to any form of chromatography in general. Okay. With all forms of chromatography, there are two phases. There is a stationary phase, a phase that stays, and there's a movable phase, the phase that moves. In paper chromatography, it is the paper that stays, surprising, I know, and it's the solvent. In our case, we were using something water soluble, so we used water. It didn't have to be water soluble. If it wasn't water soluble, I'd have to use something other than water. And the point is to pick a stationary phase and a movable phase, where the movable phase will be attracted up the stationary phase. Or if you lay it out, will still move across. You want that movable phase to move. If it's not going to move, it's not going to work as a movable phase, kind of defeats the purpose. All right. The other thing is the molecules you want to separate have to have different amounts of bonding to the stationary phase and the movable phase. Okay, not that they need to prefer one over the other, but that if I'm separating molecules A, B, and C, they can't bond in identical ways, or I'm not going to be able to separate them with chromatography. Now, chances are they're not going to bond in the same way, otherwise they'd be the exact same compound. So, we're usually really good there. We're going to talk about paper chromatography. So here's what paper looks like. This is cellulose, the macromolecule. Doesn't that look lovely? This is a small piece of the huge chain that is paper. Well, we're going to abbreviate this so we can make it easier to talk about. So here's just two little parts, okay? Two monomers of that polymer going on here. And I've color-coded some things. Do you see what I've color-coded? I've color-coded some hydrogen stuck to some oxygen. Ooh, why does it sound kind of like something important that I have a hydrogen bonded directly to an oxygen? Okay, here is red number 40, which is FD&C color, red 40, if you read on ingredient labels. It is officially called Allura Red, and it is what's in red food coloring. If you have that little red food coloring bottle in your kitchen, this is it. Now, for me, I buy my food colorings on Amazon, and I get like 16 ounces at a time because my kids are crazy about food coloring, and it's just cost effective that way. But anyway, what you're seeing before you is red food coloring molecule. Okay, we're going to abbreviate that too, and I'm going to put that over on this side. So here's my red 40, and I try to color code similar elements as with the cellulose, okay? So I've color-coded some parts there. So we have some oxygens, we have some hydrogens. We have some hydrogens directly attached to some oxygen. So tell me, is that gonna like be set up for something special? Maybe, I don't know, hydrogen bonding? Do we have that hydrogen directly attached to an oxygen? Possibly able to attach to another oxygen somewhere else? Yeah, we do. Okay, so this is why we do this in our bonding unit, because that's what I wanted you to see, is it's set up for hydrogen bonding. So here's just 4 of the potential ways that red 40 and cellulose would bond. Now, I know this from real life. If I have a sheet of paper and I dribble some red 40, you know, some food color as I'm like putting it into something, if I splash, I know it's going to stick to that paper and there's nothing I can do to get it off now because of those hydrogen bonds. It's going to stick to that. If I splash it onto, I don't know, a ceramic plate, I can wash it right off because it's not going to stick to the ceramic. Yeah, and it's not going to form hydrogen bonds to the glassy surface of the ceramic there. Okay, now so what about water? Because that's what I'm going to use as my movable phase in our use in class, and in this example, I'm going to use water. Could water do hydrogen bonding? I hope you're shaking your head yes. Like water is the very quintessential molecule of hydrogen bonding. It is two hydrogens stuck to an oxygen. Those hydrogens are ready to go for bonding, and if it finds more water, there's oxygen on that water ready to be bonded with. So water is very good for hydrogen bonding. So my model now is going to look kind of like this. See how there's going to be some red stuck to some water stuck to the paper, some paper stuck to the red, some of the water stuck to the red, like everything's going to be hydrogen bonding to everything else. And that's actually good news. This is the situation we want. We want where what we're trying to separate can stick to both the stationary phase and the movable phase. Now this alone does me no good, but we're going to see what good it can do in just a moment. But before I move on, let's review. Is red 40 attracted to cellulose? Yes, we know it is. If I spill my red food color on a piece of paper, that paper is now red. Is red 40 attracted to water? Well, yes, if I put a little drop of it in a container of water, it's now gonna start turning the water red. It's gonna mix in and start, the whole thing's eventually gonna be red, okay? Is water attracted to the cellulose? Have you ever gotten a sheet of paper wet? Yeah, because it gets wet, right? It does, okay. So yes, it's attracted. Is red 40 more attracted to the cellulose or the water? Now, what's your guess? Okay, because it actually, we don't know yet. That's what we're going to be finding out. That's the point of paper chromatography, or all chromatography in general, is to determine relative amounts of, does it bond better with the stationary phase or does it bond better with the movable phase? Okay, so here is my virtual paper chromatography. So there's my paper, and I draw my starting line, and I'm going to put some purple Kool-Aid, some grape Kool-Aid concentrated right there on that start line. Now I chose purple because I know purple's made up of two things. Purple's made up of blue and red. Okay, but we'll get to that in a minute. Do I know that Kool-Aid will stick to the paper? Well, yes, I have spilled Kool-Aid onto papers before, and yes, it sticks. There's no way to like get rid of it. So I do know it'll stick to the paper. Do I know if it will stick to water? Well, what do we mix up Kool-Aid with? I mean, this is why we're picking these sorts of things. So I stick my Kool-Aid to the paper, and then I lower my paper into the water, not all the way up to the dot, just barely where the paper touches the water. I don't want to wash the dot away. If the dot went below the water level, it would wash the Kool-Aid away, and I wouldn't be able to do chromatography with it. Okay, now what's going to happen as the water level moves up the paper? Well, it's going to move up. It's attracted with hydrogen bonds, and it literally, if you imagine it, like the molecules of water, 100 bond at a time, are going to crawl themselves up the paper. That's what's happening. Okay, is the purple dot really going to just sit there as the water moves past it? Right, no, it's not, okay? We expect the purple dot's also gonna move. I don't know how far, I'm just picking a point on my picture here, my virtual paper chromatography for it to move. So purple dot moves and the water moves because they both like cellulose and they both like water, and it all is moving. Is that really how my purple dot's gonna move? Isn't my purple dot made up of red and blue molecules? Is there any reason to think they're going to move exactly the same? No, there's not. So let's actually look at these. Let me prove it to you. Here I have on the left blue number 1, that's blue food color. For comparison, red 40, I stuck in the middle, that's red food color. And then also for comparison, I have yellow 5 over on the right, that's yellow food color. And I tried to color code similar parts. Do you notice similarities in their structures? You should, absolutely. But are their structures identical? No. And if the structures are not identical, they won't bond identically. So they won't bond identically. They won't move identically. Now I can separate them. All right. So, and I don't know which way this is going to go. I don't know which color is going to be on top. I just picked. You'll have to, try it at home. Get some coffee filter. Get some grape Kool-Aid. Okay, just cut yourself a section of coffee filter, put your grape Kool-Aid on it, lower it into a tiny bit of water, just let the water rise up and see what happens. Okay. But one dot will move more than the other. Guaranteed, that's the way that's going to work. And if you actually have watched the previous video, you actually might have already seen this, just, wink, wink, nudge, nudge. Okay. So what does this tell us? Here's the big part. This is why paper chromatography is an AP chemistry topic. You can now talk about the strength of the bonds between the color molecules and the paper and the color molecules in the water. That's why it's a pre-AP and AP topic, and that's why I discuss it in both classes, because it could be on the test, and it'd be easy points on the test if you know what's going on. And I love the year that my AP students came back from the test and they were like, Mr. Bell, and you remember in the fall when we randomly did paper chromatography for the second time, like it was on the test? And I'm like, well, yeah, I knew it could be a test topic. That's why we randomly, in the middle of whatever subject we were in the fall in AP, we did it at the same time we did it in pre-AP, because it is a valid topic in AP chemistry. So what do we know? We know in this case that the red is going to bond better to the water because it moved the most as the water moved. The blue is going to bond better to the paper because it stayed where it was more as the water moved. I hope that makes sense. They're both going to form hydrogen bonds. The red must have bonded better with hydrogen bonded better to the water than the paper, because as the water moved, it moved. And the blue must not have wanted to move a lot. It must have bonded well with the paper, and it took a lot of water to convince it to start moving at all. Okay, this is why it's an AP topic. Look at the comparison of bond strengths we can discuss now. Okay, now, to further this along, we could actually, if we wanted now separate the molecules, I could pull out the paper, dry it, cut it in half, and then I'd have the red separate from the blue. So it's a physical separation. Chromatography separates mixtures physically, okay? And separating them by the amount of hydrogen bonding they can do in this case, okay? It doesn't always have to be hydrogen bonding. It will always be some form of bonding, but it doesn't have to be hydrogen bonding, okay? But we know the one at the top bonds best with the movable phase. The one at the bottom bonds best with the stationary phase. And that should make sense. The one that moved the most bonded better with the movable phase. The one that stayed more stationary bonded better with the stationary phase. I don't know how else I can say this to make you make these connections. That's the way it works. Okay. Now, what we actually do in chemistry so we can communicate results to each other from one experiment to the next is we find an RF, a retention factor. In order to find a retention factor, we are going to take the distance the dot moved. So here my red dot moved this far, the yellow arrow. And we're going to divide it by the distance the water moved from the same start line the purple dot was on to wherever I stopped the experiment. Okay, so we divide, and it'll always be a smaller number divided by a larger number, and for some reason we just always round to the hundredths place. It's just what we do. So here it might be like 0.83. That's my retention factor. I would do it a second time for the blue dot. It would have to be a separate calculation. Are you catching that? And for the blue one, maybe it's like 0.46. The distance the blue dot moved divided by the total distance the water moved. Again, the same as the red dot there. And we rounded to the hundredths place. So that's how we calculate an RF. All RFs do is allow us to discuss from lab group to lab group. If you're both doing purple Kool-Aid, then the lab group over there and the lab group over there should have very similar RF numbers for their results. Whether it's the red on top or blue on top, I don't again know. I don't really care. You've watched the video, you would know as well. But in calculating an RF, I can compare my results to your results to my results, that lab group over there's results to that lab group over there's results. It's just a way for us to quantify the data and be able to compare results. Okay. Now, I do want to point out, and I think I've been alluding to this all the time, you got to pick your stationary phase and your movable phase well. If you don't have the right surface and the right solvent, it's not going to separate your mixture, okay? So, for example, here's an oil. I have an oil, okay? And I have two possibilities of a movable phase. I could use water and I could use hexane. Which one would be the better choice for separating different oils? Oils that look similar to the picture on the left. Well, I look at the picture on the left and I go, well, there's some parts that look like water, some parts that look like they're ready for hydrogen bonding. Do you see the similarities there? Okay. So yeah, these are parts that could hydrogen bond with water. But also as I look over on the left, I see these are parts that look similar to hexane. These are parts that could easily do LDFs, maybe even dipole-dipole, but most definitely LDFs with hexane. So really what I need to do now is decide which is the better solvent, not just based on what's possible, but based on quantity. In this case for oil, I would not want to pick water, and we kind of know oil and water don't mix. Well, they do mix a little, they'll form a little bit of hydrogen bonding, but so much of oils is not able to hydrogen bond or even dipole bond that I would want a non-polar covalent compound like hexane in order to get it to move. Water would not be a good one. It couldn't hydrogen bond with water. It could LDF bond with the hexane. So I'm going to go with the hexane because they're just, notice how much more green area I've boxed. That's what would make it a better choice. Okay, here it is with Sharpie. Black Sharpie. So you can see all the colors in black Sharpie. I put this picture here because what I wanted to point out is that water? Well, we call Sharpie permanent markers, not because it's permanent. I mean, all chemists know how to get rid of things. There's no such thing as permanent in chemistry. But we know that that can't be water, because if I used water, that black dot would still be sitting there, not doing anything. So it's got to be something else. I would assume it's something like an ethanol or methanol or something to that extent. Okay, maybe even an isopropyl alcohol, something along those lines. Okay, not water, most definitely. Whoa, don't know why that happened. I was not done and you moved on. Okay, sorry, I'll go back. Okay, there we go. And then just here's some more examples of more paper chromatography. So you can see the point is always to separate the molecules based on how well they bond with a stationary phase and a movable phase. And you have to pick those parts very carefully in order for them to work. Okay. And again, I said this at the beginning. But paper chromatography is not the only kind of chromatography. In fact, when would paper chromatography not be a good choice for separating a compound? Well, if your compound doesn't stick to paper, it's not a good choice. Because again, you need something that will bond to both your movable phase and your stationary phase. And so if my stationary phase of the paper is not something it will bond with, then I can't separate it that way. I would have to pick a different stationary phase. And therein lies why we have so many different forms of chromatography. The point of all of them is to pick the right kind of stationary phase and movable phase so that we can separate the mixture we're trying to separate. If you really don't even know what's in a mixture, you really shouldn't start with a chromatography. You could guess what kind of chromatography, or hope you work in a lab where you can just test it in all kinds of chromatography ever. But really, you kind of need to know in advance the basic parts of the mixture in order to know the right movable phase and stationary phase. Okay, so that's everything theory-wise you need to know about paper chromatography and chromatography in general. And there was a previous video where I actually showed you the lab results of paper chromatography. You should have watched that first. You really now want to go back and rewatch it. You really do. And in doing so, you now are going to be able to watch it with the theory in your head and be able to explain what you see on the screen. And that would mean you have learned, and that's the whole point. Good luck.